Okay, so I should thank the organizers for having proposed me to do this lecture, although I spent the weekend wondering why they asked me. Since half of the audience is by far more expert in the field, but probably it's the last two words that are the important part of the motivation for asking me to give this lecture. Also, I didn't know really what was the audience composed of it, so I don't know the topic, I don't know the audience, so be cool. So small warning, so it will just be some kind of a random first-order description of what a glass is. I will give some kind of a mosaic of pictures, and many of those pictures come from works that many of you here have done. They are not quoted because I didn't spend all my time quoting them, but at the end there will be a list of references for the newcomers to the field. Okay, so the questions that I would like to discuss with you this morning is, what is a glass? So here you have two pictures. One is here where you can see this very, very viscous liquid, honey-like fluid flowing in a glass oven, and there you obviously have more like a broken glass, and such broken that for sure we would all call this a solid, while we would call this a liquid. And indeed, if you start with an atomic liquid and you start at high temperature and then you cool it down slowly, and for some reasons you avoid the crystallization, either because your molecules are such that they really don't like to crystallize, or because you act fast enough such that you avoid the nucleation of the crystal, you will follow this equilibrium liquid and it becomes more and more viscous, and then at some point this liquid you will even not be really able to, it will not be able to follow you anymore, and you will fall out of equilibrium, and then we arrive in something that we call a glass, and depending on how slow you go, you can go deeper and deeper in temperature, remaining on this liquid branch, or at some point eventually you become a glass. So what is spectacular is that when you do so, if you measure the viscosity of your, let's say, liquid as a function of the temperature, so note here this is 1 over the temperature, and you rescale the temperature such that all the curve starts at the same point here, they all end up at the last one. So this is a plot that was proposed by Angel a number of years ago. But what is remarkable is this axis here, because this is a log scale. So these are the decades, so something like 14, 18 decades on which the viscosity increase while the temperature actually vary by a small 20%. So, and this can be, well, can happen in a very abrupt way, like in this fragile glass, or be more regular, like in this strong glass. And so that's, we want to understand this. Okay, so this does not only take place when you vary the temperature. There are simpler systems like, okay, so very, very viscous fluid, eventually a solid. And in all cases, you can see that it remains amorphous. We'll come back to that. Okay, so this does not only take place in this liquid when you vary the temperature, it can also take place in simple liquids, so simple that you control them only by the packing fraction. This is the case of hard spheres. So there you control by the packing fraction, or eventually equivalently the reduced pressure. And again, you can have the fluid, and there is these regions where you would have coexistence with fluid and crystal. Eventually you crystallize, but again, if you avoid crystallization, for instance, by using a polydispersed systems of hard spheres, you end up forming a glass where again the dynamics becomes very, very slow, and the system really gets some shear modulus. It really becomes like a solid. And so at the end of the day, what we want to understand is how a structure like this can be as solid, or even sometimes more solid than a structure like the crystal one. So for a moment I presented this thermal standard liquid system, even this very oversimplified one, but the same kind of physics actually take place in different other systems. Let me just show you a bunch of them. So I just discussed the case of molecules, that is systems where the typical scale of the units are of the order of 10 to the minus 10 meters, and the microscopic time scale, I mean the time it requires to move the molecule, let's say on one size of itself, is of the order of 10 minus 12 seconds. But there are systems like colloids, which are micron-sized particles in a solvent, and so they are the dynamics is equilibrated by the thermal bath that the solvent realized for these colloids. There, they are more like 10 to the minus 6 meter. The time scale to move one colloid of a micron over its diameter is typically 1 second. And then you can even go to larger scale by taking grains. Now, grains are macroscopic objects, so they will not move by Brownian motion, and you have to shake them. But if you shake them in a way that is isotropic enough, well, it mimics pretty well what you would observe for colloids. And in all these cases, when you increase the packing fraction, like here you have a very dense packing of hard disk, here you have a dense packing of colloids. In all these cases, again, if you measure the relaxation time of the density fluctuation, say, of these systems, or how much the structure reorganize, how the particles change neighbors, all these kinds of concepts. When you measure these times, well, again, they all grow significantly on several orders of magnitude when you change either the temperature or this reduced pressure that I just introduced in this, essentially 1 over the packing fraction. And so you have here again the curves for a number of liquids, but also one of these curves is for colloids. Where is it? Yes, this pink one here, and this one here is for grain. And of course, you can see that with this system, we don't reach so many decades, because if you wanted to reach as many decades starting from 1 second instead of 10 minus 12, we would need to wait for 1 million years. So be aware that when we discuss these systems, we don't really discuss them in the same range of physics as when you are above here, of course. Still, there are many, many similarities. Okay, so this is the very common phenomenology. We have a liquid that becomes solid, but there is no really evidence of order in this system. When you look at it, you could see it in this grain system or in the system of colloids there, you can really see them in real space, or you can look at liquids with neutrons or X-rays. Well, essentially the structure doesn't change much. So at that point, usually when you are in a glass conference, question starts. And the first question is, okay, but so what? Why are you wondering so much about this? I mean, how many years have you been thinking about that? So that's the very naive perspective side of the... So then an expert would tell you, well, come on, to become a solid, you must break the translational invariance. You know, that's one of the key stuff that we learn when we do equilibrium physics. And someone else would come and say, well, okay, but a frozen density profile where the particles do not move anymore, it's frozen. So it breaks the translational invariance as well as a periodic pattern. It's just that it's not periodic, but I mean, you can have tiles that are not periodic, and if it's frozen, and the translational invariance is broken. So there would be a concept of, there is some kind of order, it's not random. Okay, it's there, it obeys the Newton's law, equilibrium is there, but it's frozen, and so the thing is solid because it's breaking this translational invariance. It's just that you have an amorphous order, you don't like it because you don't recognize it, but it's there. Okay, but then what is the order parameter of the transition? Because usually when there is a transition like this, where you have some kind of broken symmetry, you like to have an order parameter that describes this symmetry, because this is how we learn thermodynamics and how we learn the way to describe this physics. And of course, finding the order parameter of an amorphous order seems like being a desperate search. And so some would say, well, but let's not care about it. You know, there is this physics going on, and but the answer is, why do we care? Is because we are all familiar with this description of phase transitions, which are supposed to describe the transition from a liquid to a solid. I mean, if we really think it's a true transition, by describing the physics of the system, I mean, the states of matter are given by the free energy minima, or let's say the maxima of a large deviation function, and you want to optimize this with respect to something, and this something is supposed to be your local order parameter. And usually you are inspired by the symmetries of the problem to find it. So here we are really in trouble because we don't know how to find it. And this is key. This is really key, because at the end of the day, what really decides whether you are liquid or solid is whether, I mean, in principle, what we learned for always, and you know, usually when we face a new problem, what is difficult is to escape what we always learned. But what we learned is that at high temperature, entropy wins, and so you prefer to be disorder, and so you're liquid. And at low temperature, energy wins, and so you would like to be in one of those minima here, especially this one. And when energy wins, it leads you to this order structure. So is it that when we become a glass, it's the same story, or is it completely different? Is it that it's because the energy wins or not? And we will see that actually it's completely different. But still that we will try to stay in this kind of framework. Okay, and then some people would rush in the room and say, come on, there is maybe no transition at all. It's just that it's becoming so viscous that you never see it flowing. But so why, I mean, you are looking for something like an order that is amorphous because you want a transition and you want this, an order parameter for this. But maybe it's just that it's so slow that you don't see it flowing, but that if you would wait for, you know, millions of years, you would see all the glasses around gently reorganizing. And then everything is fine. Well, not really, because we would still have to understand why is it so slow? And why does it turn slow or so slow so abruptly? Even if there is no transition, I mean, there's not so many phenomena in physics where you get 14 orders of magnitude by gently tuning your temperature by 20%. So even this is not an easy thing to deal with, okay? So that's essentially phrasing the problems of the glass transition. So if there are questions, please interrupt, and I will be happy to transfer the questions to the most appropriate expert in the room. Okay, so let's have a look at a few more experimental facts. Well, first, when you look at transition, usual transition, you know, you take your calorimeter. When you do thermodynamics, at least in the old times, that's what we were all doing, and you measure, let's say, the heat capacity, there is something that takes place as a function of the temperature. There is a jump in the heat capacity, which means that the dependence of the entropy with the temperature is not trivial. Something takes place somewhere. And this is a thermodynamic signature. So if it's a thermodynamic signature, the idea that it's slowly flowing, slower and slower, there is something else. That's the first statement. Then we can indeed look at the dynamics, and the typical tool to look at that is to look at density temporal correlations. And this usually people, because in liquids you do this with light, so you always live in the Fourier space. So people use what is so-called the dynamical structure factor, and this quantity typically behaves this way. So these are simulations of soft repulsive spheres. This is measured in a polymeric glass. So let's spend some time to understand what these curves are saying. You have different curves at different temperature. And so what you see, so let's start with this blue one here. So essentially what this tells you is, okay, at short time it's 1, and 1 means that nobody has moved. So this is compute, I should say, this is compute between time 0 and time t. So between time 0 and time 0, essentially nothing has changed, and this thing is 1. That's what it means to be 1. And if you wait a very, very long time, well, then it goes to 0, which means everybody has moved. Then you should ask me, yes, but by what amount? This you decide. You decide when you set the value of the wave number here, 2 pi over some length scale. So essentially, this tells you that after these times, everybody has moved more than the length scale associated with this wave number. And usually you take a length scale that is, well, let's say the size of the molecule or a fraction of the size of the molecule that you are interested in. And so, well, you see that this correlation function, well, first, everybody essentially dependent of the temperature relax pretty fast on a certain amount, and then you have a plateau that develops, and you go down to 0, and the size of this plateau elongates, and eventually becomes very, very, very long when you cool down your system. And this is true here in the simulations, or you have the same kind of observation in this polymeric glass. So one thing that you can do is say, okay, so we can define the typical relaxation time of my material by typically measuring the time at which you have, let's say, decorrelate by 1/2. And this is what we will call the relaxation time. And if you plot this, because again, this is in log scale, you have that this relaxation time increases like mad, again, many, many decades for a modest range of variation of the temperature. But this curve tells you also another thing. You see that these are not just, nice exponential decay. There is something, the shape of the curve is a bit more tricky. There is a rather fast relaxation, and you can imagine the little molecule is moving on very, very small distance. And then to move further means further than the distance that you have selected, well, it takes some time. And it seems the molecule is a bit trapped. Okay, and that's one of the idea that somehow in the glass, the constituents are trapped by each other because it's too cold or because it's too dense. Another thing that it tells us is that because these are so-called stretched exponential, it means that these curves, they seem to tell you that there is not just one relaxation time, but actually a bunch of them. You can see this as a sum of many exponential with many different relaxation times. And so it's not that there are just one simple processes going on. There are many processes going on in parallel. Okay? This is further seen if you look at, let's say, somehow the response. We are at equilibrium, so you can look at spontaneous fluctuations or response. Essentially, it contains the same message, but it presents things in a different ways. So again, the two systems, here soft repulsive spheres, and here it's glycerol. And so this is the dielectric response. Okay, let's say that it probes again the density fluctuations. And what you see is that the response is far from being just one. So these curves are different temperatures, and it's far from being just one peak. So the peak is the main response frequency. So that would be essentially this relaxation time. But these things are very broad. Again, these are log scale. So for example, here, it means that we have a response on 9 decades of frequency. So again, 9 decades of frequency. So there are really many, many processes going in these systems. Okay. So there's a broad spectrum of relaxation and response time, and the relaxation time increases like mad and is responsible, of course, for the increase of the viscosity that we described just before. Well, in all these systems, it's very hard to really look at what's going on. What are the molecules doing? And that's why colloids and granular systems are interesting, despite the fact that, as I said at the beginning, they cannot really probe the same range of time scale in the system. And so let me show you what happens when you look at the system. So there was first a tour de force here. This is in a polymeric glass, and this is dielectric response spectroscopy. So this is time, and this is, well, space, actually 3 lines, but I mean, that was not bad. And again, this is measuring the response of the system as a function of time. And what you can see is that these signals are not random. There are really correlation in time, but also in space. When something happens at some place, something happens later here or here. And so there are spatial-temporal correlations in these systems that are not trivial. It's not just like, in a gas. Now, if you look in colloids, it's the same thing. Here, what it shows are the particles of the colloids that are the most motile. So you look at them, you measure the displacement, you use confocal microscopy to do so. This is a 3D suspension. And, well, you can see really that there are clusters of particles that are really moving faster than others. And this is in a granular system. So the granular system, again, you have to excite it, otherwise nothing would take place. So this one is in a fluidized bed. And you have your beads, and they are gently, so there's a turbulent flow going on. It's 2D, and these beads now can rearrange because of these turbulent flows that is supposed to mimic the thermal activation or agitation. And again here, colored, so the red are the mobile particles, the blue are the static one, and again you see it's very heterogeneous. So there is a way to quantify this. I don't want to enter too much in the detail, at least not now, but there is a way to quantify this, and you can measure how many particles contribute to these correlated events somehow. And again, when I say that this is moving more than here, I have to say, okay, but it's moving on what time scale? Because, of course, everything is moving. It's all moving in here. So the question, so you would say, okay, let's consider some time scale t, and let's compute, whatever the methods, how many of these particles are correlated. And what you see for a given temperature again is that there is a time scale which is not short. There is a time scale on which these motions are maximally correlated. And this time scale again increase when you decrease the temperature, and the number of units that are correlated also increases when you decrease the temperature. And you have the same kind of curves, not as clean as here for the molecular liquid, but in a colloidal suspension or in these agitated grains.
Excuse me, Olivier.
Yes?
So what are the boundary conditions in the agitated grains?
It's something like a round container.
Okay, so next question, don't you have huge finite size effects?
In this system, yes, probably we have, yes. In this one even also. No, sure, there must be. These functions, well, especially, okay, so that's an expert question, but especially the decay here can be severely controlled by finite size effects and also temporal effects. Since you are computing a variance, I mean, you need realizations of the events. But the good thing is that because you see them, you actually know how many events, you know the signals of which you are computing the variance. So this allows you to, you cannot make quantitative predictions. I would not play, fitting Power laws here and there. But the fact that this grows systematically with time and with the packing fraction for grains is clear. Okay, and indeed, despite all these finite size effects and temporal finite time effects, etc., there was an attempt to compute this size of correlated regions in all these different systems. And this leads to this curve, where the size of the correlated region in number of particles is plotted as a function of the log of the relaxation time divided by the microscopic time scale. That is the 10⁻12 seconds for the molecule, the 1 second for the colloids. And there are here a large number of liquids, but there are also the 2D grains, and there are also the colloids somewhere. I don't know where they are, but they must be there. And what you see is that, well, all these data actually fall down on one given curve. So there is a very strong correlation between the slowing down of the dynamics and the size of these correlated domains in real space. So that's, again, here I'm just listing experimental facts. And finally, the last experimental fact, which is at the origin of the conundrum, is the fact that if you measure now structural quantities, for instance, you compute, so here I don't know how much you know about liquid state physics. So let's say you compute, you want to measure the structure, so what you compute is, if I'm a particle here, what is the probability of having a particle at a certain distance from me? And so this will give you information about your structure. So if you are in a gas, this is completely flat. I mean, the probability is completely random. And so the distribution of the particle is completely random, and so there will be no structure in the function that I will plot, which will be the probability of finding someone at a distance from me. It will be completely independent from the distance, just related to the density. It's not true if you are in a crystal. If you are in a crystal, well, just nearby me there's nobody, and then one lattice size later there is for sure someone. So you would have a curve that would be systematically periodic. And then if you are in a liquid, it looks like this. That is, there is a higher probability to find someone here, and then less because there are some kind like shells around you because of steric effects. And then progressively it becomes flat at long distance. The curve here are just shift for the clarity of the figure, same here. But what you see is that in this molecular liquid, when we tune the temperature between this 300K and 90K, and the viscosity increased by 14 orders of magnitude, essentially, these curves are the same. And this is true for the liquid, this is true for colloids, and this is true for grains. So this is very clear that at least with this measure of the structure, that is what we call pair correlation functions, because we only look at particles 2 by 2, we can do things more elaborated, there is no signature of anything going on in the structure. And we'll come back to why is that such a problem. Well, of course, you can say, well, but this is just two particles correlations. Maybe the correlations are by far more tricky, and they must be if there is some kind of amorphous order. So you can look at higher order structural parameters, and so there are different ways of doing this, and I will not describe all of them. One is more like, okay, I believe in amorphous order, and I try to find signature of the fact that there is some kind of order, although amorphous. So it's a little bit like looking in a chaotic signal, if you want, in time. It's chaotic, but it's perfectly deterministic. So there is something, and you try to look for this something. Or you say, well, no, maybe, you know, the crystallization is never so far away, and you look more like at structures that belong to the onset of crystallization. And this is, for example, what is done here in this colloidal suspension, where what is shown here are clusters of local regions where you satisfy the full icosahedra symmetry, or what is called here defective icosahedra. It does not have all the particles around. And well, for two different packing fractions, you see here that part of the system has decided to converge locally to this kind of structure, and then when you increase the packing fraction, you see these ones coming in. And so maybe this kind of disordered arrangement, but specific arrangements, are playing a role in the slowing down of the dynamics. Okay? Okay, so summary of the phenomenology in one slide. When you are liquid, you have a structure like this, but the particles can move around individually, and if you look at who is moving more than others, well, it's completely random. And you relax your dynamical structure factor very fast, essentially on one time scale, which is the time scale of this diffusive motion. That's a liquid. And then when you go to much cooler systems, supercooled liquids, well, the structure is the same, but for some mysterious reason, or maybe it's not the same, that's all the question. For some mysterious reason, the dynamics is not at all the same. The little thing is completely trapped, cannot really go away, does not diffuse, or you have to wait the age of the universe. And to do so, it does it collectively, by little groups. And in the meantime, as I say, the structure doesn't change. So that's the real question is, why does this dynamics change so much? Okay. So, questions? No question. So now we have to try to answer this. And so the starting point are the Newton's law. This we all know. Nothing else. So we have an Hamiltonian describing our liquid with the kinetic energy, the potential energy, the interaction potential, which can be of different kinds, either the real one of a liquid or model liquids like Lennard-Jones, a purely repulsive one like the WCA. You can take repulsive harmonic spheres, you can take hard spheres. Your choice. And then you have the Hamiltonian equations resulting from this Hamiltonian. So you see that because of this simple equation that we all know, well, the dynamics is entirely encoded in the structure. The potential only depends on the position of the particles. So the forces only depends on the position of the particles. And the forces decide the dynamics. So that's why it's so puzzling. It must come from the structure. And we don't see it. And that's where we are facing the struggle, where we are really struggling. Now, the good thing is that because we have the equations, because we have big computers, and probably this will be one of the output of this workshop, well, it allows for very large molecular dynamic simulations of these equations, where you can now follow really what's going on. And I will conclude with very nice pictures obtained doing so. And because we are interested, so I showed you at the beginning that when you cool down, the system remains liquid, you avoid crystallization, you've got a supercooled liquid. So of course the crystal is somewhere there, but we avoided it. And then if you really go too far in temperature, then you will fall off of equilibrium. But this increase of viscosity that I showed you, that I described you, is already present when you stay in this supercooled branch. And so this supercooled branch, if you exclude the crystal over there, you can still deal with it as if it was an equilibrium system. It's a metastable state, but I mean so stable that, because the crystal is over there, that you can really deal with it as if it was equilibrium. And so you can also do Monte Carlo simulations to probe configurations. So these are the tools that people from the glass physics are using every day. So what can you do with these equations, except at staring at them? Well, there is a first theory that was proposed quite a long time ago. We have experts in this room, which is the so-called mode coupling theory. It really starts from the microscopic equations and tries to derive an equation that would at least describe the behavior of this dynamical structure factor. That is this first fast decay, then this plateau, and then the second step decay, and the plateau elongates when you decrease the temperature. At least that would be nice to get that. Because this can be easily defined from very first principle from the position of the particles. You define your density field, you compute the correlation, you write it, you have your equation, you inject them in the dynamics, and you're supposed to get equations, a dynamical equation for that. Well, of course, you have to somehow reduce the number of degree of freedom, as we always do in statistical physics, and we always pay a price for that. And the story here is particularly a bit involved, so I will of course not enter into the detail, but the idea really is that you want the dynamics of this, and the dynamics of this object will depend on interactions, let's say, between the dynamics of between the same objects, but taken at different wavelengths. So you will have coupling between the dynamics of these different modes. That's why it's called mode coupling theory. And this coupling will depend on the static structure. That is, if I give you the structure at one time, and it's given forever, or I sample it, then I know this, and I should be able to predict the dynamics of it. Okay, so when you do this, you end up with an equation which so far it's not so complicated. It's a second order equation in time that gives you how much this change. So you see, it looks somehow this is an harmonic oscillator, not much more than that. But here, this harmonic oscillator has some kind of a damping term that has a memory kernel, and the devil is in there. Because when you write this memory kernel, you see that indeed it couples, as is illustrated on this figure, two different modes. You have to integrate this over all modes, and there are amplitudes for this coupling, and the amplitude depends on the structure. And when you do so, you are already making a bunch of approximation, and so it's not sure that this will describe perfectly well what you observe. So let's see what it gives you. Well, it's quite successful. I mean, this theory has been criticized a lot, but a statement should be to say that it is already quite successful, since it does predict this kind of shape for the evolution of this quantity as a function of time. A ballistic fast relaxation regime, what people call beta relaxation, and then the decay to zero for what is called the alpha relaxation. And it makes also prediction on how you reach this plateau, how you escape this plateau. And people has compared this with experiments in colloids and in other systems, and it was pretty good. Unfortunately, the theory fails in the sense that when you plot this relaxation time alpha as a function of the inverse temperature, it increases on many decades, and it even diverges. It diverges, and it diverges too early. That is, as compared to the simulation of the same system would see the viscosity escaping this divergence, so it diverges too early. It will lead to a plateau here, an infinite plateau, which you would not observe in real life. Okay, that's life. Now, it's fair to say that that was the, let's say, old way of doing it, and that some people in this room are still working hard to make better the approximations, and working hard, increasing some kind of level of closure that are implicitly there in these equations, you can make it better. That is, this plateau, you can push it further down in temperature. So this is still ongoing research. So that's the mode coupling theory. You can see it as a mean field theory in the sense that the system is homogeneous. There is no spatial dependence of the dynamics of this quantity. And this is what it provides you. It does not really eliminate you on the mechanisms going on. That's for sure. It's quite abstract and formal. How are we going to group these minima if we want to say, okay, but maybe some of them are equivalent, but which ones? Okay. And then, of course, if you take an Avogadro number of particles, it becomes a complete nightmare. You have a terribly complex energy landscape. And so what is needed at this point is a theory for characterizing this surface. And this is possible, actually. There are a number of mathematical tools to do that. Of course, I will not enter into the detail. So either there are some models where you can solve it exactly, or you can approximate the surface and try to count the minima, the maxima, the saddles, etc. And this has been done again in mean field model. And here are the results. So this is, let's say, my surface cut. And so when I'm at high energy, what I see is that all my critical points in this surface, essentially they are saddles. That is, you should of course, you perfectly understand that this surface is not just 2D, it's completely n-dimensional, I forget to say, but it's not to machine learning guys that I will tell you that high dimensionality matters. You have this, so at this high energy, well, you only have saddles. That is, there are always directions that you escape. You cannot stay, all fixed points are unstable in terms of dynamical systems. And so it flows, that's the liquid. And then you decay the energy, and at some point, many of these directions that were going down becomes flat. And you are in some kind of a world where you never know if you should go down or up. And in this world, everything is slow. And on top of that, you have many of them. And so you go from one thing where you don't decide to another things where you don't decide. And this somehow topological transition or geometrical transition in these energy landscapes actually corresponds to the transition where the time scale diverge in the previous theory. So that's good. There is a connection between the two. And this is characterized also by a system that is full of soft modes. I mean, the system is able to go anywhere at zero cost in this phase space. And then you keep cooling down, and now they become minima. But you have plenty of them, an exponential number of minima. And then you still cool down, and at some point, there is no more minima. Or at least there is just a non-extensive number of minima, and so the entropy that counts these minima, that I will later call configurational entropy, is zero. And so if this happens, then you would say, okay, that's the ideal glass. That's where the situation would be a true transition. Okay, so that's a nice picture, but I mean, can we evaluate it? Is there a way to compute this? And well, yes, there is. So the trick is the following. And it is both a numerical trick, but also a theoretical trick. But the idea is that, okay, there is always this problem that these minima are supposed to be this amorphous order that we don't know how to characterize. And then there is this brilliant idea that maybe we don't know what this order is, but the glass knows. So if I take a glass, and I say this glass is an amorphous order, and then somehow I couple it to another glass, I use this glass as a field coupling to the other glass, then this one will want to be like this one. And I can use this trick, and conceptually you can think of this as the replica trick, or you can even do it numerically actually by coupling your molecules from one glass to the others. But the image that you have to keep in mind is that if you look at a liquid, and when you go from the liquid to the crystal, the transition, the signature of the order is very clear. Now, if you look at the situation we have to deal with, take one configuration of the glass and just let it evolve in time. So if you are in a liquid, well, then what you can see is that when you, as a function of time, your liquid will change. I mean, the position of the particles will not remain the same. While in a glass, because the dynamics is very slow, somehow there is some kind of, this structure here is the same as the one before. And so the idea is that you are going to quantify the level of order in the glass by how much this configuration overlaps with the previous one. And this way of thinking has allowed us to make really immense breakthrough. And doing so, you will define the order parameter of the glass as how much it doesn't change. So it will be a dynamical one in some sense. Okay, so, well, no, it's not a dynamical one. I should be more precise because, okay, of course. This is because I'm an experimentalist, so I probe in time. But a theoretician would not do that. He would sample the glass. It would sample the glass according to the equilibrium distribution and ask itself, if I'm in a glass, all configurations should be more or less similar because I'm trapped in some amorphous order. And if I'm in a liquid, one configuration differs a lot from the other. So it's more like sampling than time. of course, when you run it in time, you also do that, but you don't need time. It's important because it's a static theory, this one, so I should not use the words dynamics. Okay, so of course I thought about it when I saw this figure. And then when you do this, you can do this for many, many, many pairs of configurations, and you get plenty of overlaps, and then you can look at the distributions of these overlaps. Okay, think that this is like if your overlap was your magnetization, and you will look at the distribution of the magnetization, and when you do this, what you are plotting is actually the large deviation function of your order parameter for a magnetic system, and so this is the equivalent for this system here. So this is minus the large deviation function is the free energy, and according to this theory, what you find is that, well, you have the liquid where this quantity is essentially always 0 because two configurations taken at random in the liquid differs too much, while in a glass it takes some value which is of the order here of 0.6, and then when you decrease the temperature, well, you have these curves here that, because it's a mean field theory, that progressively goes down, and you have a second minima that develops, which is a metastable state, and then it goes down, and maybe at some temperature it reaches exactly the same probability as the one of the liquid. And so you see we recover the picture of a classical first order transition at this level, except that here these are not really energy. What changes is really the number of different configurations, because what will decide the fact that your overlap is large or small is how many different configurations you have from which you sample. And so it has a taste of something which is more entropic, and this is here what is, again, we recover this configuration entropy that I introduced before. Now, if you plot this configuration entropy as a function of the temperature, well, it goes down and reaches 0, as was somehow anticipated in the description that I just did before. And the order parameter, which is the value of this minima here, well, is discontinuous, as you would expect for a first-order light transition. Of course, this is a rather abstract construction, and for sure, again, it's completely mean field in the sense that you consider the system as completely homogeneous, there are no spatial fluctuations, and so for sure, we don't include yet all these ideas of faster regions, slower regions that I described when I was describing the experimental facts. But okay, it means that there is, on one hand, there is this mode coupling theory that tries to describe the dynamics and the relaxation time with some success and failure. And then on the other hand, we studied the energy landscape. If you take a model system, you can compute these minima, and you get a picture where you have these saddles that becomes flat, and that becomes minima, and then the number decreases to 0. And then it happens that if you take, I forgot to say that, if you take a model of hard spheres in infinite dimension and you compute that exactly, you find this. So the hard spheres in infinite dimension realize this mental picture that we had about this energy landscape. Okay. Of course, as I just said, all this is mean field, and it would be nice to have some information about what's going on in the real world, at least, let's say, 3 dimension, maybe 4, 5, but not infinite. So the key point is that we have been, well, in the mode coupling theory it's less easy to see, but for the energy landscape picture, it's very clear that everything was based on counting minima. And if I count minima, it means that I can define them. And not only that I can define them, but that the system stays there for a time that is enough so that it matters. If they are always moving between minima because of they are going over the barriers, well, then this concept of minima is still there, but maybe not as useful. And so in mean field, you are protected because the barriers are infinite. In infinite dimension, the barriers are infinite, but in the real life, they are not. And so these states are not well defined. And there are activated process. You can nucleate, and nucleation is crucial when you crystallize, so why would it be crucial here? So this, okay, so now you are now starting to make hand waving theory, because as soon as you quit mean field, you have to use your hands. So we suppose that there are still two time scales, a vibrational one in the minima, and then there is this activation one, and this is really inspired from what we know from nucleation, and we expect that you would go above the barrier with a time that is exponential in the height of the barrier. And there was an argument made by Adam Gibbs, which is the following. So now we are thinking real space. So it's getting really inspired from the kind of pictures that I showed you. And the idea is, okay, let's imagine that we have n particles, and then you have these correlated regions of size small n. This size will depend on the temperature. And so you have n over small n of these correlated regions. And because they are very correlated, the particles are not free to move independently in these regions. And so the number of effective degree of freedom of one region is not at all the sum of the degrees of freedom of all particles. They somehow, let's say, they behave like a solid body. Okay, so they just have a few and fixed number of degrees of freedom that is small. And then you can count how many configurations this gives you access to in your whole system, and that's a very simple calculation that is here. And what you see is that the number of configurations, or rather the log of the number of configurations, the configurational entropy associated to that, would go like 1 over the size of these regions. Okay. Then you make another hand-wavy argument to say, okay, if these regions have to rearrange or to change, well, they will have to go over a barrier. And well, the more there are particles in there, the higher the barrier will be. I never completely bought this argument. I just repeat it here, but okay. And so you say that the height of the barrier is proportional to the size of the region. And then you get that the height of the barrier goes like 1 over the configurational entropy. And if you get this, you immediately get that your relaxation time. So now this configuration entropy, from what we know at the mean field level, this one just goes, completely regularly to 0 at some temperature that is called Tk. Well, then you would have that the relaxation time would behave like this. Yes, sorry. Okay, maybe, okay. The relaxation time would behave like this and would diverge at this temperature Tk that is far below the one of the mode coupling theory. Okay. Now, the problem is that this might be a correct picture at low temperature where these minima are more or less well defined, where the barrier are still there. But then when we will increase the temperature, the events corresponding to this jump over a barrier, so this argument about one region reorganizing, etc., independently from the others, will be less and less true. Things will couple together, and so the picture will become more and more fuzzy, as always when you higher temperature, and progressively this picture of barriers is completely wrong. So somehow, to summarize, we have, again, this relaxation time that increases like mad when you decrease the temperature. We have a theory that is this mode coupling theory that makes diverge this time scale much too early in temperature. And then we have another picture that is related to the structure of the landscape and the fact that the number of minima vanishes exponentially at some temperature Tk. That would predict this dependence with a divergence at Tk, a true phase transition at Tk. And anyhow, we cannot probe the system much further than this temperature where the system falls off equilibrium anyhow. But that's the situation, the current situation. Okay, then there is the next progress is to take this idea a little bit more seriously and to try to build up some kind of a nucleation theory of this amorphous order. That's the next step. So maybe a small recap about the classical nucleation theory, where, well, you have a metastable equilibrium, a stable equilibrium, there is a barrier, you want to nucleate some event, so you have a droplet of the stable state inside the metastable one, and this has a size L, and then you compute the free energy corresponding to this configuration as compared to the homogeneous one to know if this will grow or shrink. And when you do this, you see that there is a critical nucleus size. And if you have something that is below, if your droplet is of size smaller than this size L star here, you will come back to no droplet. And if the droplet is larger, if the spontaneous seed is large enough, then you will, you will follow this part of the curve and you will invade the whole system. Okay, can we do something similar here? So we have all these minima. So we select one, minima A, and then we put a droplet. But now in this droplet, it's not that you have to put B. You can put B, C, D, E, F, G, and I need all the alphabets of the world and more. So now, and also all these minima, they are more or less at the same energy. So there is not really a difference in energy. We can forget about this. But now the main difference is that here there's only one state, and here there are plenty of states. So if I transform this into state A, I lose a lot in terms of entropy. A lot. Here I have so many configurations that are possible. And so that will be the cost this time. The cost will be an entropic cost. And this is really where there is a shift, a paradigmatic shift between the classical figure of why you become a solid, because at some point, low temperature, you favor energy. That was what I was saying at the very beginning. Here, at some point, it's a matter of entropy because of this number of minima. That's the key message maybe to remember. Okay, and then you do the same. You evaluate the free energy of this configuration. And you see, again, you have a cost because of the interface. This is the same cost as here. But because here, essentially in here, the main difference is really the difference between these two levels. But you have one state and one state. So here there is not really any entropy cost. Here, the energies or the free energies are the same. But there is this huge cost because of the configurational entropy of the droplets. And then you can plot the same curve. Oh, sorry. Now you have essentially the same curve. But the point is that now when you go away from here, well, you don't know where to go. Because here also you may have a droplet that does the same thing. And if it does the same thing, it will not do with B. It will certainly do it with another letter. And so at the end of the day, you have all these droplets. I mean, this is really a naive picture, but you have all these droplets that tries to do this. They have to obey this equation here and to favor the configurational entropy. But if they get large enough, whoops, they want to grow. But then there's another one that also wants to grow. And at odd with crystals, it must be another state. So hence this picture of a mosaic, which is the idea that you have many of these states that tries to grow when they are larger than L star. And okay, that's again, nobody really never saw that in the real world. It's a picture. But it's interesting because this length scale, you can compute it exactly using this formula here where delta F becomes 0. And you see that this length scale goes like 1 over the configurational entropy. So this length scale would go to infinity when the configurational entropy goes to 0. And so this picture of nucleation driven by entropic reason and not by energetic reasons, these pictures leads you to a diverging length scale where the number of minima in your energy landscape goes to 0. So this points really at the true phase transition taking place there. And the time scale, which also grow like this length scale exponentially, will also diverge and even much faster. As a matter of fact, the fact that there is this exponential here means that the length scale doesn't need to be so large to explain the huge change in the time scale. And actually, well, no, not yet. Okay, so this is a nice mental construction. But I mean, what does it predict? So of course there are precise calculations behind there. You can test it in different models. And so these are essentially the output of this theory. Well, first, there is this idea that below some temperature, there are these regions in the energy landscape that traps the system from some large amount of time. And this is responsible for this plateau in the relaxation function. And the systems become somewhat rigid. Now, we know that such metastable states are exponentially numerous, and that allows us to define this configurational entropy. But at the same time, the fact there are so many of them allows you to still go from one to another. So somehow you are trapped, but you always escape, but you escape to something similar. And so that explains also this long plateau that you will have in your dynamics. And now it happens that for some systems and some models where we can compute it, this configurational entropy goes to 0 when the temperature reaches some temperature Tk, smaller than the one at which all these minima appears, leading to a true phase transition in an ideal glass. Of course, this has yet not really been computed in a real system in finite dimension, etc. I mean, this is still a picture, and it's validated in the mean field theory of hard spheres. But I mean, it's not clear that that in a real system where heterogeneous in space will come to play, this will survive actually. It predicts a static length scale that is supposed to diverge at Tk, and it's nice because it makes the correspondence between the log of the relaxation time and the configuration entropy. So something relating the dynamics to a property of the energy landscape. And that's probably the major result coming out of this theory. Okay, how can we test this theory? So you use numerics. Very, very heavy numerics. Experimentally, it's really tough because this length scale is likely to be pretty small, maybe a few particles diameter. So it will be very, very hard to say anything about is this growing length scale really significant in an experimental system. It's not desperate, but it will be really hard. Numerically, you can investigate here polydispersed hard spheres in 3D. You use a lot of tricks to do so. And you can actually compute in 3D this free energy, or also called the Franz-Parisi potential, that is the distribution of these overlaps. So you probe configurations. It's some kind of a Monte Carlo, but don't try doing stupid Monte Carlo, you will not reach it. For different packing fraction, and what you see is that indeed, well, when you are at low enough packing fraction, well, you have a nice convex curve here, and then when you increase the packing fraction, at some point, well, there is a tendency to develop this kind of non-convexity, but because we are in finite dimension, there is somehow the Maxwell construction that plays and resists it. But you see, this would somehow here define the glass state. And so that would be the configurational entropy that you could measure. And when you measure it in different systems and you compare it to different ways of measuring this length scale L star, that is also called a point to set length scale, depending on how you define it, how you measure it, well, you have strong indication that indeed this configurational entropy is decreasing, and is going maybe somewhere to zero around here. So these are, I mean, serious confirmation and ideas about the fact that, yes, it seems that even for a system in 3 dimensions, this number of states is decreasing, and that this decay is responsible for maybe not a true transition. We have not reached it yet, but it has the taste of it. Yes. Okay. Of course, there are some issues. One key issue that came to us quite recently was actually appeared because of an algorithm that was used to probe those configurations. This algorithm is called the swap algorithm. So the idea is very simple. You do Monte Carlo, but instead of just doing standard Monte Carlo, and there's a C missing here, where you just try to move your particles a little bit and then you reject according to the proper weights to satisfy detail balance. Well, you can actually add moves that are not real in the sense that they would not at all mimic true dynamics, but they do still satisfy detail balance. And what you do is that you just try to swap 2 particles of different size. Remember that they have different size because these systems are polydispersed to avoid crystallization. And it happens that when you do so, you are able to equilibrate the same system at much lower temperature, significantly lower. And that's really bizarre. That's bizarre because this idea of this barrier and this minima and this thermodynamic picture and this length scale that diverge is completely controlled by the idea that everything is getting collective, like the fact that crystallization is something collective and that there is a long-range amorphous order. But if that's true, and if that long-range amorphous order is there and is responsible for the slowing down of the dynamics, then how is it that by just exchanging 2 guys, I completely find the door to escape this slow dynamics? That's really bizarre. This is a long debate. I want you to feel it bizarre. Actually, there is an argument that goes around this. And maybe I will give a little taste of it. Okay, but that's really, that's uncomfortable. Then again, looking at the dynamics, you remember that in the real system, we see these dynamical correlated regions, and we could measure the size of these dynamical correlated regions. And now we are super happy because we have a length scale, a static one. And so we can compare both. Well, unfortunately, when you compare the dynamical one and the static one, when I was telling you that there are small lengths, this is, let's say, 1 particle diameter, and so this is the static length, and the static length, you see, it goes to 1.8. That's not much, huh? It's far from diverging, but okay. And the dynamical one is growing faster, much faster. So also, the static one is there at all times. It's a static quantity. The dynamical one, remember that I insisted on the fact that depending on what lag time you use to define the displacement of your particles, the peak of this quantity that was measuring the size of the correlated regions is increasing with the time. And so, and then actually, then it decays. So there is a time scale on which the displacements are maximally correlated. If the length scale controlling the physics is static, then there should not be a time scale on which these are maximally correlated. So these two phenomena are not easily connected, the least to say. And that's something that the random first order theory does not easily capture. Okay. So now we can come to the conclusion, which are, okay, what are the open issues? Why are we in this room? So first, we have this nice theory. I mean, I should insist that it's also nice because it understands where is the mode coupling theory diverging. I mean, there is some kind of a consistent picture in mean field, let's say. And now we move to this image of nucleation, this so-called random first order theory, which tries to adapt this image of the energy landscape to the real space. And there is this length scale that emerge. And so either this length scale grows and diverge. And so it follows this bona fide RF40 scenario. And okay, that's the image of a true phase transition taking place at some point. Or it gets stuck. It can get stuck. It can get stuck at some rather small value, as it seems from the experimental and numerical observations, because the particles in there are completely constrained kinetically. The things would like to move, but because there's no space, I mean, it's stuck. All these little blocks are already too rigid, like somehow in a polycrystal. And so you're stuck there. And so this would be essentially dominated by the fact that you are dynamically constrained and you never go to the transition that would be predicted when L star diverges. You just get stuck there. And now it's again the pure dynamics that would control everything. So this conundrum, whether it's dynamics or thermodynamics, is not completely solved at all. So what are the really related issues? So we use this trick of overlap to have an order parameter for the amorphous order. But it would be nice to identify the amorphous order. So you guys of machine learning who are so good at classifying, you could tell us, this is the amorphous order, this is not. This is a cat, this is a dog. Okay. Is it really purely amorphous, or are there hidden cats and dogs in there, that is known structures? This is also something probably you could help us. Then this is about the structure. Then what about the dynamics? I mean, if this is stuck and you need to move, maybe the others on the side will help you. This is what is called facilitation. That is, well, maybe I didn't say enough about this idea of constraint. You are constrained and you move only if your neighbors assist you in moving. So that's the idea of you facilitate the move of the others. So what would be those mechanisms in details? Are there defects? Like in a crystal, if you have this image, if this image was this image of a polycrystal, you would tell me, yeah, there are defects here, and then the defect would move, and so the boundaries would move, and progressively you would realize the true phase transition. But what are the defects in an amorphous order? Because if you're amorphous, then it's even harder to define the defect with respect to that. And then, of course, you are really like a solid here. So there are also these long-range fields, like the elastic fields, that can play a role. And this is complete. I don't have time to elaborate on this, but this is a very serious question. And this could be the excitations that play a role in the system. What is the relative importance of these collective effects that seems to be there according to the more thermodynamic picture and the growing amorphous order, and the more local facilitation things that takes place. The fact that if I'm stuck here, but if this one moves, then the other will move, the more real space image. And on top of that, maybe not all the glasses are really the same. Maybe what happened is that there is a true glass transition at TK somewhere over there. And then the relative importance of the collective effects and the local facilitation, this doesn't need to be universal. The idea of a phase transition is. The idea that there is facilitation can be. But now the relative amplitude of these two effects, probably it's likely to be system dependent. In some sense, those one here may not see early that TK is there, and then when they start realizing it, woof, they have to climb very, very fast. And those here realize it a little bit earlier, and this would depend precisely on the relative importance of these two effects. So maybe this non-universal stuff would explain what is called these different fragilities of glasses, but this is complete speculation. Okay, so if it's system dependent, and that you have to run simulations like this one, for all those systems, plus the kind of simulations that I report here, that I will describe in a minute. For all these systems, there will be an amount of data that even people from machine learning can dream of. So just to conclude with this slide, I mean, what is missing is really to understand what is going on in the system. I mean, we would like, again, to come back to see what's going on. And how are these excitations correlated, and what's, once we are in this very, very supercooled liquids. So a first exploration of this was done in actually a granular system, where we could identify really elementary event when a particle somehow, instead of purely vibrating permanently around the same position, does something a bit different. Here also, machine learning could help in recognizing this, what we call cage hop. But cage hop is not going, just around a neighbor. You don't have enough place to do that. It's just something a little bit different, but different from vibration. And so it was hard actually to have an agnostic definition of this, but okay. Once you have this, you can look at them in space and time. And this plot here represents you somehow, this is a projection of many times between 5,000 and 5,500. And it's colored by time. And it tells you where the particle hop. And what you can see is that once you have started hopping at some place, you are likely to hop more in the neighborhood. So there is indeed something that is related to, facilitating each other. Okay, and this is a 3D view of the same process. And so you see there are these kind of avalanches. When something starts, it lasts for a while, then it quiets, then it cools down, and then again another start here. And you can study the dependence of this pattern as a function of the packing fraction or the temperature. And, well, you get different pictures. This has been done recently with a much larger system, 2D and 3D soft repulsive spheres. So these are really huge simulations. You will hear, I think, about them. I think it's today, Camille? Yes. And it's essentially the same representation. And again, you see that there are regions where the thing stacks on top of each other. And this, it's even clearer in the 3D representation. I flipped it to match this one. And there are regions which have never relaxed here on several relaxation time. So now we have access to everything here. I mean, really the microscopic organization of the glass is there, the structure and the dynamics on 5 tau alpha. This is for 2D and 3D soft repulsive spheres. As I say, it would be nice to do this for many, many different glasses and try to see whether what we can call facilitation, that is the fact that one helps its neighbors, etc., is more dominant or less dominant in one system or in another. And maybe that would explain the different ways the viscosity of the system increase when you decrease the temperature. I will conclude with just a list of reference. So I guess the slides will be put somewhere at some point. So that's why I did that. So of course, I did not put all the possible references, as you can imagine. I had to make a choice. It's more the one I had to look at when I decided to make when I had to do this lecture. I never decided that. So there are two mandatory starting points if you really want to enter this field. Is these lectures actually by Andrea Cavagna, Supercooled Liquids for Pedestrians, which I strongly recommend. It will go through all the details of the supercooled liquids up to 2009. And then there is a little bit later this theoretical perspective on the glass transition by two of our organizers. Then for mode coupling theory, I strongly recommend to start with this very nice short paper of Lisbeth, who is here in the room, and that tells you everything about mode coupling in very simple words. Then you can go to this if you want to learn it a little bit deeper, and then you enter the nightmare of it, and there are thousands of papers. For the energy landscape, I think these papers by Sastry and co-authors to give you an intuition of the importance of the energy landscapes are key. And then if you want to count the minima and their properties, you should enter this or the one with Gérard Benarous, and that's more like also the nightmare corresponding to this one for this field. For the mean field theory of simple glasses, I think there is this book that just came out, Theory of Simple Glasses, but you have also this paper here in the Review of Modern Physics that gives you a pretty wide idea of this field. And this is a paper where you can see how to compute this configurational entropy numerically. And then for the random first order theory, that is this idea of nucleation of the amorphous order, there are the originals paper by Volines. There are a number of them, but let's say these two here, this one here is very good. And then you have this book. And then I recommend these two papers here. This one is very good because I mean, it really discuss the assessment of the theory. And this one is a very short one, but very recent. It's still on the archive. And it really discusses these problems that random first order theory has to deal with to cope with the dynamics. And then for experimental and numerical facts, I just quoted a few here, but of course there are plenty of them. This one focuses on dynamical heterogeneities. This very recent one that will actually appear in the same issue of the Compte Rendu de l'Académie des Sciences is some kind of trying to show how grains, colloids, and liquids behave similarly and differently. This is more for...
Does it exist? Or?
Yes, it will be on archive tomorrow afternoon. Some figures were taken from that one. And this is more about computational results. And this is the 30 milliseconds in the life of a supercooled liquid from which I took the last figures. And I think Camille will talk about it. And you will have nice movies saying really what a glass is doing. With this, I thank you for your attention.